So so you'll have to submit a report for this assignment, and it's through mesh convergence. So basically, whenever we run a model in Abaqus, the accuracy of our outputs from that model will be somewhat dependent on the density of our mesh. So a denser mesh will lead to kind of higher accuracy, but you eventually will reach a threshold whereby increasing the mesh any further doesn't really give you any further accuracy. So so for your lab report, you'll have to basically plot a load. So you have to kind of run your model for a number of different mesh densities, and then plot those mesh densities against some specific output from your job, and that output is up to you. But we'll go through those steps. So we have to do this for the hinge model. So I'll just run through the hinge model in full, actually. Okay. So if in the in the assignment brief, you can actually run a Python script which should bring you, I think, most of the way through the model. I haven't run it myself yet, so I'm not sure how far it'll bring you. But to run that, you can just download the zip file and then just go file. Where is it? Run script, and then run your Python script. But nevertheless, I'm going to run through this in full. Okay, so first of all, we have to create the hinge part. So I'll call this whole. It is deformable, solid extrusion. Approximate size, I think, was 0.2. Yeah, 0.2. Okay. So we'll sketch the hinge. Uh, 0.04, I think. If anybody sees me making any mistakes, just let me know, because doing this in real time isn't ideal, obviously. 0.04. Okay, so that's our sketch done. Middle click again, and then we want to extrude it 0.04. Okay. Now we need to sketch on the other piece of the hinge. So we can use this tool here, create solid extrude. Select the face that we want to sketch on. So we'll use this face, and select the vertical on the right. If there's no vertical on the right available, you have other options. So select vertical on the right. Okay, so now we can sketch. Okay, so we want to put a few constraints in here. Want to make this line horizontal. Okay, so there's the constraint. We want to make these two lines equal length. Hold shift down, middle click. Okay, so you can see the constraint added. So then we need to add this circle thing. Okay. Add another circle here. Add a few constraints. So tangent. So these lines need to be tangent. No click. And here again. There we go. Radius then of this circle. In the report, he kind of changes it. He sets it as the one thing and then goes back and changes that. I'm not going to bother going through all those steps. I'm just going to put it in right the first time. Okay, 0.012. Yeah. 0.012. And this length is 0.02. Okay. Okay. And then another constraint here, concentric for these circles here. Like, yeah. So concentric. Okay, and you can see that constraint added. So that's that. That's fine for sketch. So middle click to finish the sketch. Middle click again. So now extrude it. So it's extruding the wrong way at the moment, so we just want to flip that here. Extruded 0.02, I think. Just check that. Yeah. Okay. Okay. So now we want to add this hole here, which you can see in the assignment brief again. So to do that, we have to we need to add a sketch plane. So tools, datum, point, enter parameter. This line 0.25. So this is basically 0 to 1. So 0.25 is 25% along this line. I'm going to put another one on this side as well, which will come in handy later on. And one in the middle, halfway between these 2 points. Midway between 2 points. Okay, so there it is. So now we want a axis line, 2 points. Okay, and we'll use that axis line and one of these points to create our sketch plane. So we use point and normal, select our point and our normal. There we go. So here's our new sketch plane. So in the assignment brief, again, we actually create our sketch down here, and then we upload it. But there's no need to do that. It's just adding to the workload. So previously we created, to add this flange, we created create solid extrude. So the opposite is create cut extrude. So we use this tool, create the sketch plane. Click on the sketch plane, which is this vertical on the right here. Okay, so now we can sketch here, and we can use this point as our center point. So sketch here. Okay, so just grab the dimensions of this. Zero 0.003. Okay, so let's extrude this. Middle click again. So you've different extrusion options here. So let's use up to face. Okay. And then select the face that you want to extrude to. So this one. Okay. So that's that part made. So then in the report, or sorry, in the assignment brief, we copy this part and basically remove the hole. If we assign material properties now to this part, whenever we copy the part again, those material properties will carry through. So it just saves us a step. So I'm going to assign material properties now. So create material, steel, elastic, 200 e to the 9. 0.3. Okay, create a solid section. Okay, assign steel to that solid section. Assign then this solid steel section to our material assign section. We don't want to create a new set. You can if you want, but there's no need to. Okay, middle click. Solid steel section. Okay, so that's material assigned. So now we can just copy that part. Copy, and I'll call this solid. There's no hole in it. Okay, so we want to delete that hole. So in features, datum, delete, and that deletes all the dependent or children features. So as I said, the material property should have carried through. So section assignment solid like this. Yeah, so that has been assigned. So that just saves us a step. Okay, so now we want to go to assembly. We'll bring in. Oh, sorry, we use a pin as well. Pin. Okay, so we said discrete rigid in the assignment brief. If you do this, so if you set it as analytical rigid, it just saves you a bit of workload because you don't have to mesh it or anything. So that's the mistake I made last time. I thought I had selected analytical rigid, but I had selected discrete rigid, and then I didn't mesh it at the end, so the job obviously wouldn't run. So yeah. So analytical rigid, revolved shell, approximate size same 0.2. Continue. Okay. Okay, just get the dimensions here. Okay. Okay, so 0.012 and 0.6, or sorry, 0.06. Yeah. Okay, middle click, put in a reference point that we use later. Okay, so that's all our parts done. So let's go assembly. Bring in our instances. So bring in the 2 hinges. Auto offset. I'm going to keep them as dependent. Okay, so now we put in our constraints. Yeah. Face-to-face constraints first. Flip. Yeah. Middle click. I have to offset. 0.04. Okay, real quick. Coaxial constraint. Constraints, coaxial. Flip, I think. Yeah. Okay. So then last constraint, H to H. Constraints H to H. Middle click. There we go. So now let's bring in the pin. Okay. Constraints, coaxial. Okay, cool. So we just want to center that. So you want to obviously measure how far this length is here, and then kind of shift this whole instance half for that length this way, so it's centered. So to do that, they gave us it in the report. Just in future, if you're doing your own stuff, you can measure that by tools, query, distance, and then measure that distance. Okay, so translate instance, middle click, start point 000, middle click, endpoint 2. Okay, cool, that's done. For constraints, this comes in handy if you're making any changes to your parts later on. Let's shift it back. I'm just going to shift that again. Middle click, middle click. Okay. So what are we on now? Steps. We've 2 steps. Well, we've our initial step that's already there, and then we have a contact step. Okay. They said not to change, so in the incrementation you can leave this as 1, and that's probably fine. But just to give yourself, give the program the best chance at solving the problem, just you might as well always set that to something low. It's automatic, so it'll tend towards the maximum value if it can. Okay. So that's our first step. Second step is the load. We're going to apply load to this phase in this step. Continue incrementation. 0. Okay. Okay, so then yeah, so we have our steps here, right? So initial contact load. So we want to, I think in the report then or in the assignment brief, it said to change the field output requests. You don't really need to do this, but just so you know how to do it. So right click on field output requests manager, and then you can kind of go into either step here, or you can access it through either step individually. So you can go field out requests and you can go into it that way. So say if we wanted to change these field output requests in the load step, we can click on load here, edit, and these are the values here that we're recording, and it's for the entire model. But you can change these if you want, leave them out or add new ones in. I'm not going to bother changing that. I am going to add a history output request for the sake of demonstration in the visualization module. So to do that, I'm just going to create a new set, and we're going to create a history output request for that set. So tool set create edge. Okay, so this edge, say, right, middle click, output request, create, it's in the load step, edge, continue, on model, set, edge. I've only defined one set. So let's say we want to record von Meek stress, which is something that comes in handy. Okay. So I'll demonstrate that in the visualization module when we have run our job. So now we just want to apply contact or interaction properties. So let's create an interaction property called no friction. Okay, mechanical tangential behavior, frictionless. Okay, so as before then in the clip instructions, find contact pairs. Find contact pairs. Okay, so we're going to delete a few of these. Okay. Okay, so that's contact defined. So now we want to set up our loads and boundary conditions. So boundary conditions, create. So here I'm actually just creating a generic boundary condition, right? If you wanted to create and I'm going to apply it to each step then afterwards. If you wanted to create a boundary condition for a specific step, you can just do it as I was saying, the same way as field output requests. Just go into whatever step. So we've 3 steps. Initial contact load. If I want to do it in initial step, create my boundary condition here, create. But I'm just going to define it earlier. Yeah. Boundary conditions, create, fixed displacement. Okay. So I'm going to fix this face. Again, I'm not creating a set. I'm not going to bother doing that. It's no harm to, but I have that unticked. Middle click. I want to fix it in XYZ direction. U1, U2, U3, XYZ. Okay. Now I want to fix this pin, or yeah. So I want to make sure it doesn't slip, at least in the initial step. No slip. Continue. So select the regions I want to apply. So this is analytically rigid, right? So I can just select any point on this reference point, and that applies to the whole body. It's totally rigid. That wouldn't work for deformable bodies, such as the 2 clips. Okay, fix it in X, Y, Z, and it can't rotate either. So then I want to constrain this this hinge. Great, constrain displacement, point, middle click in XYZ. Okay, so now, so these are just created generically, right? So actually they were created in the last step. So I just right click the manager, just, but I can propagate these back. So now it's created in the initial step. Oh, shit. Okay, so whenever I apply the load at this point here, I want this clip free to move in the X direction. So we're going to edit. So so in initial and contact, it can't move in the XYZ direction. But in load, I want it to be able to move in the X direction. So I take that off, edit. But if I go in here, That's still applied. So then no slip. I want this able to be moved in the X direction and to be able to rotate around the Y direction. Let me just check that. Yeah, okay, right. That's right. So, okay. Okay, so now we're good to go. Dismiss. So we just want to apply the load. Great. So pressure. Pressure. Apply pressure on this face. I think it's like minus e to the 6 or something. Yeah. Minus 1 e to the 6. Okay. You can see that's applied there now. So I'm just going to go into this manager here and just show you. So so you see that's defined then in the load step, right? Okay, so now that's everything defined, hopefully. Might be an error or two, but we'll come to that. So now we just want to mesh it, right? Okay, so they're dependent instances, so we want to mesh in the part module. So I'll mesh this guy first. So I can't mesh that at the moment, so I got to split it up into sections. So let's do that. So we want to create partitions. So tool, partition, cell, define cutting plane, point and normal, point, select the point, select the normal, done. Then I'll just, yeah, then I want to divide this up as well. Define cutting plane, middle click, point and normal, point, and select all. Okay, so that's ready to go. So at the moment, there's two different mesh settings defined for each unit here. You can tell that by the different colors, right? So I want to change that. So I use this tab here, which you can assign like high level mesh controls, and here you have finer level kind of mesh controls. So using this, select the entire piece, middle click. So sweep, so hexahedral meshes or elements. Sweep, medial axis. Okay. You can play around with that, like, you know, there's nothing to stop you using whatever mesh that you want to. Okay, this one. I'll split this up too. I'll do this a different way just to show you. Tools, partition. So extend face. Well, we got to select the cell first. Yeah, oh yeah. So, middle click. Okay, so same as before. So let's apply the same meshing technique then to both of these units. Same as before. Middle click. Sweep. Medial axis. Okay, cool. So now we want to assign. We want to seed these guys. So use this button here to apply global seed density. So you set that here. We'll just roll with that for the time being. Okay. And then this one, do the same. Okay. Okay. So now let's mesh these parts. So use this button, mesh, middle click. Okay, so that's meshed. And I'll do the other one. You can also see, so just whenever you're doing your report, right, you're going to have to vary the mesh density. So one way you can do that is by increasing the seed density. So use a higher number of seeds. but you're going to have to record how many elements are here. And you can see that this is displayed down here. So there's 1,000, roughly 1,000 elements in this. So we'll do the same for this guy, mesh, real quick. And then you can see here there's 900 elements applied to that. Okay, so that's it, I think. So we'll run the job, create hinge, continue. Okay. Okay, hopefully this works. It ran in the last one anyway, and there's a video for that. So, okay, so you can see it's running. Okay, so that completed. Right, so you can see completed. You can also go monitor. So you can look here at it iterating through the number of steps. So do you remember I set the initial step size to 0.1? So it started at 0.1, but then it was able to kind of tend towards a higher step size. So it goes, this is it increasing. But it's always good to start with something lower. Yeah. Okay. So now let's look at the results. So it's two ways to look at the results. You can go File, right click on that, click Results, or you can just go into the Visualization tab, which is here. Same thing. Okay, so here's our model in the undeformed state. So let's look at that. Okay, so here's our model. So at the moment we're visualizing von Mies stress, so you can change that here. So you have kind of, it's like a higher order, like a kind of, there's a hierarchy here, right? So you have stresses, and within stresses you can look at a number of different things. So we're looking at von Mies at the moment. If you want to look at, you know, stress in XX, it's this, and you can change that whatever you want. Displacements, you know, X direction displacements, whatever. But von Mies is really what you want to be looking at. Okay, so here we go. To move through the steps then, so yeah, so you can see we're at the last step here, right? So step load increment 6, and there are 6 steps. So we can move back manually like that, or we can actually just use this button here to kind of fly through the whole thing. So just, you see that looks all deformed, so just the scale is off there. Tools, common, uniform, lower. Okay, cool. So that looks fine now. Yeah, so initial state, and we're running through the model there. Okay. So there's a number of different things that you can plot. So I'm just going to fly through some different things that you might use in your report. The last of which I guess will be the most important. So, so we want to create XY data, right? So tools, XY data, create, and we have a number of different options here. So remember, we've stored history output requests and field output requests. So history output requests, to give an example, do you remember I created a one called Edge? So if you loaded them, these. Oh yeah, so I select the whole edge actually. So there's a load of different elements there. But I'll just plot a few of them. Plot. Okay. So yeah, so you can see then von Mies stress. You know, for each, you know, through time. And then time is unitless as well, right? So that can mean whatever you want. That's just the start and the end of the step. So and this is for each of the different elements. Okay. So we could maybe plot. We can like plot a path along this part, and then plot strain. Or plot some variable along that path. So to do that, I'm just gonna hide 2 of the instances here. So part instances, solid. Remove. Okay, so just use this one. Okay, so let's create a path first. So tools, path, create, age list. You can do whatever though. Continue after. Shortest distance. Okay, that's not a very good example, but you get the gist anyway. So this is plotted by shortest distance, right? And the first point I clicked was here, so it's gonna go. This is our path. So I just say done, right? Okay. Tools, XY data, plot. No, sorry, create. Path, continue. So I've only created one path, so that's not there. Select whatever step you want to plot it on. So 2 steps, contact load, and then within load 6 increments. So it's the last increment. Okay. Your variable. So 1 meter stress here. Plot. Okay. So that's along that path then on the x-axis, stress along the y-axis for that step. Okay, so I think the main thing then for your reports is looking at the maximum stress, right? So where is this again? Oh yeah, this one. Let's. Okay. Okay, so here we can see then stress, min stress, right? So I think what would be a good idea is for your reports, right? So you're going to run, several mesh densities, right? So you're going to have to kind of go back and forth, and you're going to plot this value here so this max stress value on the y-axis, and then your mesh density on the x-axis, and you should find that eventually this value will converge, and kind of no further increase in mesh density will have a real effect on this value. Okay, so that's the first thing, right? So I'm going to go back now. So to change your mesh density, so there's a number of different ways you'll do this, right? So the first thing, just broadly change your mesh density, like by global seed size. So at the moment there it's 0.004. So let's reduce that to I don't know, to apply, delete meshes. We'll apply our mesh again. Middle click. Okay, so there we have finer mesh now. So you'll run this, and then actually I won't run that because I didn't do the other one. So that's okay. So hold. What did I say? 0.3 on the last one, yeah. Okay, delete mesh. Okay, finer mesh. So let's run this job again. Submit, and it should take a little bit longer now. And again, then so you can see here on the first So you can see on the first one there, which I think was solid, wasn't it? It's like 10,000 elements there. In the second one, there's 3,000. So you're only gonna take one of these values because you're at a max von Mies stress on one of these hinge points. Pick whatever one you want. Just give a reason for picking it. So you're going to plot this value against the max von Mies stress that we saw a moment ago. So that's still running. Okay, so we're in step 1 there. So now we're going into step 2. And there's 6 increments. We're on increment 1. And again, just a reminder for anybody doing Abaqus projects, you can increase the speed here by parallelization and using multiple processors. But I don't know how many processors these computers have, so I'm not going to change that. Okay, that's completed. Results. Okay. I remember which one I hid last time, but I removed. I think it was the other one. Okay, so max stress here is whatever. So then, I can't remember what it was last time either, but I think that's pretty clear. So first thing you need to do is change the global seed density, and then plot the number of elements in one of these parts against the max stress value, until that kind of converges. You don't have to plot. You don't have to use like max stress value. You can use whatever you want. Like if you wanted to create a path, say, like we did a moment ago. So say use 3 elements, like that maybe, and then like average the stress along that path or something. Whatever you want. But this is probably the most convenient, I think. That's what so second thing, then we want to go back into mesh. You had to change your element type. So again, this one here is for like high level mesh controls, right? So we have hexahedral meshes, tetrahedral meshes, whatever, and your technique or whatever. So you have more controls in here. So at the moment we're using element type C3D8OR, and it's set to change that to C3D8. So to do that, so at the moment it's set up for reduced integration. So we tick that off. So we have this element which should be more accurate. So we run the model again, with this element type. The way you want to do that is up to you. If you want to kind of repeat the whole mesh convergence using both element types, or if you want to, with one element type, do your convergence study and then look at, look at one mesh density with 2 different element types or whatever. But obviously, the more work you do, the higher results you're gonna get. And you could also experiment with a few other things here. So you could use, you could change the quadratic. You could. I don't know. Yeah, that's probably it. You do a few different things. It's up to you. You probably find a few YouTube videos and stuff on that. So secondly, then, so that's 2 things. The other thing is, if you increase your mesh density locally, so if you have a really high mesh density close to where you're measuring your output variable, but you were further away from your output, from where you're measuring your output variable, say over here, mesh really coarse. This coarse mesh shouldn't really have much of an effect on where you're measuring your output variable. So the third thing we need to do is we need to increase our mesh density around where we're taking our output variable, which is this circular rim here, right? So to do that, just going to remove that. So we want to increase mesh density around here. So we need to partition this face a bit more. Partition cell. Okay, middle click this one. Sorry. Partition. Define coding plane. This one. Use 3 points. This point. This point. This point. Middle click. Okay, so you see I've divided that there. And I'm going to do the same here. Middle click. Oh, sorry. Yeah. Select that. Middle click. Use 3 points again. Middle click. Okay. I'm going to assign the same meshing technique, which is sweep needle. Okay. Okay, so I want to refine my seed density. So I want to have like a higher number of seeds closer to the edge here. So this is the global seeding, global seed density. So I'm going to change that back to 0.45, which is what I had. Okay. So now let's refine seeds on certain edges. So I'm going to select the edges. So you can see at the moment there's like one seed there at each edge. Okay, middle click. We're going to use a bias. So we need to switch some of these arrows around here now. So flip bias. We want them all pointing inwards. Okay, by number, say. So number of elements, let's say 5, bias ratio of 2. Okay. So you can see now that we have, it's going to vary on depending on like the bias ratio that you use, but you can see the elements here are closer together than further away, right? So we've higher density elements closer to the whole edge. Okay, so if we mesh that, then I'm holding that down here, right? So anything in this tab here that you see with like an arrow means that there's more options. So this one, mesh part, middle click. Okay, so you can see here now that the element size here is smaller, closer to the rim of the circle than it is kind of far away. So you can play around with that. You probably want to increase that a lot more than I did. So that's the third thing. Okay, so we've 3 things. So just again to say that. So we want to first of all globally change our seeding density with this. So, and then the lower this is, you know, we're going to have more elements in our part, and so we're gonna keep on changing that. So say if I run it with whatever, I run the job, I see what the max stress is, or whatever variable you want to measure, and then I come back, I increase my mesh density, and then I run the job again, I see what the max stress is, and I'm plotting those two values on an XY graph. And you'll find that eventually, when you increase your mesh density to a certain value, you're not going to really have much of your variable, your max stress value is not really going to change that significantly after a certain point. Second thing is then change the element type in here. Not sorry. So run this element type, then unclick this, and then run this element type. If you want to run more stuff, that's great. And then lastly, increase your seeding density locally, and see if that has much of an effect. And that's it. Yeah, that's it. So that was pretty quick, but I think we ran through everything. Does anybody have questions and stuff? And again, just a Python script as well. You can just go file. Where's run script? Yeah, run script. And run it. No questions? Cool. Okay, guys, we'll call it there then. This is recorded, so I'll upload that later on.